The last speaker is Honza Král, who comes from Czech Republic. Honza is a Python programmer and Django core developer. In delicate words, he states that he prefers backend rather than frontend. Since 2013, he works for Elasticsearch, the search and data analysis engine, which he will cover in his talk. Honza Král, Beyond the Basics of Elasticsearch.
Hello. So I was asked to give a talk about Beyond the Basics because apparently everybody's tired of the introductory talks. So let's hope that we can make that happen. But just to sort of give me an idea, how many people here have any sort of experience with Elasticsearch? Okay, a fair number of people. That is actually great. That was what I was hoping for. Okay, but so we'll cover the basics really quickly, because we sort of need the theoretical background to move on to more engaging topics. So search is a very old problem. It was actually first solved hundreds of years ago without even any thought of a computer. But the approach that we take to search inside Elasticsearch, or when we read a book or anything like that, is still very much the same. It is based on a data structure that's called the inverted index. It is called inverted because we are not using the file names or the document IDs as the keys in the index. Instead, we are using the content broken up into little pieces, tokens or terms. So in this case, we have 4 files, we have 5 words, and this is the exact same data structure that you find at the end of any technical or any factual book. And it works exactly the same way. So if you want to, for example, search for something that contains Python and also Django, what you do is you locate the words in the directory on the left side here. And notice that for that reason, the directory is sorted, so we can very efficiently locate the word that we need. And then we just follow the list of documents that contain this word, the so-called posting lists. And we just merge those 2 lists, which are again also sorted, so we can do it very effectively. And we just essentially return the documents that are contained in both lists. So this is search in a nutshell. This is all what we do, or better said, this is the basis of all that we do. The inverted index does not only contain this, it also contains additional metadata that will be very important for us as we go on in this example. The most important part is that for each file, we have some statistics. For example, we know that in file 2, Python is mentioned 3 times. We also know that there are 3 documents, 3 files that mention the word Python at all. And these are important stuff. But let's step back a little bit. So we have an inverted index powering a search. And funnily enough, we can also use the inverted index to power something that we call an inverted search, something that we call Percolator, which is exactly what I mean by reverse search. In regular search, you have your documents in your index, and then you run the queries. With Percolator, with reverse search, you index the queries, and then, well, this is awkward, then you run the documents. So essentially, it will give you all the queries that would have matched this document if the situation were reversed. And this is a very handy functionality. There's much use cases out there. The simplest one is alerting. So imagine that you run a classified website or any ad-based stuff like Craigslist or something. So a user searches, and she wants to find all the ads that selling a house with this many bedrooms in this neighborhood, and nothing comes up. So the user, she might want to save that search and be alerted whenever there is a new ad that would fulfill that criteria. With Percolator, that's easy. We just register the query inside Elasticsearch, and then we run every new document past it. And when it matches, we know that we should alert this user that the ad that matches her criteria has finally come. So that's the alerting, and that's fairly basic, and we want to go beyond the basics. So we'll look more on the more advanced use case of classification. What I mean by this is we can imagine that you have a CMS. You have articles, you have categories, and it is fairly trivial to define a category based on search, a dynamic category. So you will have a page, a site in your CMS that will have all the articles that mention Python. And that part is easy. What is usually the hard thing is, given an article, give me all the dynamic categories where this article actually lives. And again, that's something that the Percolator can do very well for you. So let's start with something even a little bit more complex. So this is a query that will look for events in whose location is inside of the city of Warsaw. I just pre-indexed all the cities in the world into an index called shape. So I have the document representing Warsaw there, whose field area actually contains the crazy polygon that represents the borders of the city of Warsaw. So this is just essentially saying, go through the events index and look at the location field, and if it falls within this shape, then it is a match. So just looking for all the events inside Warsaw. So this is how we can find it and later tag it. What also we can do is we can start with the assumption that every language has a few words that only exist in that language and in none other. I do think that for Polish this is a little bit too much. I think if we just count the number of S's and Z's, it would be enough. But what we can do is we can just get all the words that are specific for Polish, and say that if a document contains at least 4 of those, then it is probably actually written in Polish. So this is a search that can find all the Polish documents in your index. And it is here also to show that in the Percolator we can use the entire power of Elasticsearch. Any query that you can run, you can also use as a Percolator. So if you put all of this together in the convenient API, we then show it a document. So we have a document in the events index. It is of a type conference, and we ask Elasticsearch to percolate on it. We have a title. I heard this is a good conference, so that's why I use it for an example. Though I had to cheat a little bit because the description was in English. But Google Translate thinks that this is more or less what it said. I have no idea. And then there's some location. Don't try to look it up. This is not Warsaw, but let's skip over the little details. And this is the result that we get. We get that it is in the city of Warsaw. It's most likely in Polish, and it most likely deals with Python. And you can all probably imagine what a query would look like to say that something is about Python. You just look for some keywords again. You look for Python or Django and programming, or .py, or that Brendan Rhodes is speaking. Like there's many things that you can search for that will indicate that the event deals with Python. So what you can do is, before you index this conference, before you put it into your index for other people to share or to search through, you can run it through the Percolator and automatically add these tags into the document for better experience for the users. So they can now see very easily what are all the cities, what are all the languages out there, and can filter, and you can provide them with much better search experience. So this was the first use case. This was Percolator. This was here just to show that search doesn't have to be just one direction. It can be reversed too. So let's look at another use case that we have. The crucial difference between search and filtering, between what a full-text search engine will do for you compared to more traditional data stores like SQL databases or Mongo or stuff like that, is that we not only know which document matched your query, but we also know, and we will gladly tell you, how well it matches. And we can give it to you in the order of relevance. So how does this happen? What is the magic behind the curtain that makes this work? So the crucial term here is tfidf, which is actually represented by this don't, and that is actually not as crazy as it looks. TF stands for term frequency. It's how many times is this term, this word, present in a field, in a document. So that's what I said earlier, that Python is mentioned in file 2 times. So that's 2. And IDF is the number of documents that contain this word compared to the number of documents in total. So essentially, how rare this word, this term is. Is it a very common one that exists in every single document that we have? Or is this a very specific term that only exists in the very few documents that I want to look at? So that's this. Then Lucene, the library that actually sits below Elasticsearch and does a lot of the heavy lifting, adds some more stuff on top of it. It will, for example, add a normalization factor to account for the field's length. Because if you find Python in a much shorter field, for example, the conference title, it probably means much more than if you find it in a body of a book, because there are so many things in there that just by sheer statistics, the chances are higher that you will find something. So we should account for it. It also uses a slightly modified version of the tfidf formula. But this is very good, and it works very well for text, and usually there is no reason whatsoever to try to dabble with it. But sometimes it is not enough. Imagine that you have a website, let's say some buffer overflow or something, where programmers can ask questions and receive answers. And users can vote which answer and which questions are actually good and which are bad. Or you have the reputation of the asker or of the people giving the answer. So you have more information than Elasticsearch. You have a quantifiable datum that identifies whether a document is good or bad. Or you want to search for a hotel in London and have those that are in the center of London come up on top. And as further away as you get from the central ideal location, you want to define how the score, how the position in the results should decay. And of course, we are firm believers in composability and flexibility, so you can do all of these things at once. So let's take this apart. So this is a very simple query. We're looking for a hotel that has Grand Hotel in the name. We want to have a room with a balcony. So if the facilities array, if the facilities list contains balcony, we want to add 2 to the score. So we don't want to filter by it. We don't want to limit ourselves to only the hotels with balcony, but we want to favor them. And that is a crucial difference. We also look for central London. I love London for these examples because you can easily identify it by the 0 in the latitude. And ideally, it will be within 1 kilometer of this position, and as it goes further, use the Gauss function to actually decay the score. Going back to essentially this picture, Gauss is the black line. So we want to use that sort of progression, or digression in this case. We also have the popularity. So people have voted on our website how they liked certain hotels, and we want to take that into account. We want to favor the hotels that have been rated positively. So we can do that. We just inform Elasticsearch that, yeah, I have this field, it's called popularity, and just take it as a factor when you compute the score. And then we add a little random numbers. That's always a good idea, right? Now, the reason there is, and this is actually from a real example from semi-real website, is to sort of randomize things so that new things pop up. So you don't always see the same hotels, and you have a chance to discover new things. So that is very important. What you can also do is you can just strip all of this and just write a script yourself. We'll even give you the access to the tfidf or the original score of the query, and you can do whatever. But in this case, we just want to take certain conditions that, if met, should boost the document up in the result set. We don't want to sort by any of these conditions, because that would completely destroy any relevance that we have. We want to compromise. We want to take everything into account and combine it for the optimal result. Going back to the buffer overflow example, we don't want necessarily the highest rated question on the top, but we also don't necessarily want the question that matches the closest to what I typed in. I want a combination of that. I want a question that matches fairly well, not the best, but fairly well, but is really highly rated. I want it to be at the top. But also, if something is really, really high quality but barely even matches, I don't want that on the top. So I took both of these numbers. I used some fancy mathematical formula like multiplication. I don't know, addition. There are papers written about this. I don't understand any of those, but there are ways to combine these to actually make what you want happen. So that's the relevancy. Now we need to take another intermediary step to get where we finally want to be. And that is aggregations. That's another thing that Elasticsearch can do, and that's another thing that generally any or most databases can do. It is essentially the power to divide your documents into buckets and run a calculation over all the documents that fall within each bucket. In Elasticsearch, we are very explicit about this. So you can define the bucket. This is a bucket per country, and for each country, we define bucket whether the user has been signed in or not, and for each of those, we again define each bucket based on the browser that they use. So we can use 3 levels of bucketing. We can nest the buckets inside, and finally, we just ask for the count of documents. So this is just for a website. We can immediately know where people are coming from and what are their behaviors. You can immediately see some differences right here, because people are really good at recognizing patterns and noticing abnormalities. And that is a very interesting piece of information, because we want to be able to replicate it. And one reason why we want to replicate that is to power recommendations. So our next example is a recommendation engine. Let's say that we have an eShop, and we have users' buying history. So we have 2 users. User A purchased product A and product B, and user B purchased product C and product D. So we have 2 documents, and for each user, we have a list of products that they bought as terms, as just normal words. And we want to do recommendation. So let's say that I'm user A, and what would you recommend to me? So one way to do it is just do a simple aggregation. Ask for the most popular product that I haven't bought, but people who have bought the products that I bought liked. So that's very simple. We just query for the users that like the same artists. Okay, the example switched on me a little bit. I'm sorry. And we just ask for the most popular artists, excluding the ones that I already liked. So this is fairly trivial, and it also doesn't work. Imagine if I asked you all what website you use the most. I assume that the first result will be Google. That doesn't mean anything. Everybody likes Google. But what is more specific for this group compared to the general population is that you probably visit GitHub more often than regular people. So that would be something. That would be significant. And that is what we will actually do. So we have another type of aggregation called significant terms. And how it differs from the term is, it doesn't look for the most popular. It looks for the most popular in this group compared to the background. So it hooks into the statistics, into the metadata that we have in the inverted index. How common is this word? How many times is it in which document? And all of these stuff. And uses it to give you something that we call uncommonly common. It is something that's common in this group, but the fact that it is common is in itself uncommon. So in this case, we only look at the abnormalities. So if for the users that like the same things I like, what is specific about them? What do they like more than what people generally like? And this essentially allows us to identify the meaningful connections. We don't have to follow everything, but we can actually deduce which connections are meaningful and which are useless, either because they're very generic or because they're very exotic. And this we can do very easily. What we can even do is we can use this as one step in a graph algorithm. So imagine that you have a graph algorithm. You're looking for connections between two concepts. Let's say that you have concepts in Wikipedia. So we have again two documents, and the terms that we are looking at right now are all the titles in the document and all the links from the document. And with this algorithm, with this approach, what we can do is we can, for example, find what connects two completely different topics, but only follow the meaningful connections. So don't follow the connections that are super generic, like people, or United States, or Poland. So many pages will point to those. So, which makes them essentially meaningless. Because just the fact that somebody is connected by something like this, that this is a person, and this is also a person, that's not interesting. So that is something that applying just this significant terms aggregations, you can get there. So essentially, this approach, the combination of relevancy and aggregations, looking at multiple things at the same time, is how we look at the world. That's the example I gave with the Google and GitHub. If I look around, it's not interesting to me that there are 200 persons, but there is something more specific. It's more interesting to me that I see Python programmers. I immediately go to the more specific part. If someone were to ask you when you get home, like, who was at the conference, you will not say 250 people with average height of 170 centimeters. That's not relevant. That's not interesting. You will say that there were 250 people, 230 of which were Python programmers, 20 of which were interested in learning Python. So that is the meaningful connection. That is not just the most common fact, it's the most interesting fact. And this is a generic approach that if we learn how to do that, it improves everything we do with data. Especially if we have a lot of data and we don't have the luxury of looking at everything at once, but we need to select. So we can use this approach. So we have a little bit of a time, so let's go through one last chapter, and that is how to improve or how to introduce relevancy into geoqueries. So let's say that we're looking for places inside of this polygon. The way this works in Elasticsearch by default is we overlay it on a grid, and we essentially index all the cells, all their IDs, which are some weird hashes, that this polygon touches. So then when we look at what the difference between two polygons, whether they intersect or whether one is contained within the other, we just essentially run simple text queries. Like, I'm looking for a polygon that contains all these hashes, or contains at least some of these hashes. And that is good, but it only gives you whether something matches or doesn't. It doesn't give you the score, because the number of hashes that match, that's not relevant. It's relevant to the size of the polygon, but not necessarily to how relevant it is. So what we can do is we can use a simple trick that statisticians have known for a while. We say that we encode all the polygons as n hashes, when n is the same for all the polygons, no matter the size. And we sample those randomly. And that's what we index. And then when we run the query, we just count the number of matches that we get. So the higher the number of matches that we get, the more specific the polygon was to our search. Because without this, if we had the polygon for Europe and for Poland and for Warsaw and for even finer areas, we wouldn't know which one is the most interesting. If we use this simple approach, we know immediately, because the most specific one, in this case also the smallest one, will actually match the best. So that is it with my examples. And if you have any questions, now is the time.
Hey, thank you for a great talk. I would like to ask you on, is there any clear roadmap for Elasticsearch, or what are currently you working on for the next couple of weeks, days, months even?
So we are currently working on Elasticsearch 2.0. So the big exciting features there will be, what I like the most is something that we call bucket reducers, which is currently when you do aggregations, you get back the results, but there's nothing you can do with them. And also we have no concept of order. So some aggregations are out of our reach. For example, any derivative aggregation. So what is the trend? Are things growing or going down? So that's what bucket reducers will allow you to do. It will essentially introduce another layer that will sit on top of the aggregation and will aggregate the already aggregated data, which will allow for interesting things like predictions, derivatives, and stuff like that. That's my favorite feature for 2.0.
Thanks.
Any other questions? There's one there in the back.
Yeah, so my question is if you know about something or somebody doing something interesting, analyzing Python source code with Elasticsearch, and about some large code base, to learn something about some large code base.
So there's this company that indexes a lot of code that actually uses Elasticsearch. It's something like GitHub, GitPlace, GitHub, yeah. Yeah, so they actually index and search over a lot of code. They have over 40 terabytes of data in it. I don't think they use it actually to learn anything about the code. They just want it to be searchable. For code analytics or statistics, I don't know of anyone who is currently doing that.
But it sounds like it's doable and you could learn
Absolutely.
something. Right?
Absolutely, it's just a question of the analyzer, which is the process of how to go from the text to the words that you put into the inverted index, which needs to be special for programming languages because it needs to be aware of the syntax and what is a keyword and what is the definition of a class and things like that. But it is definitely doable because once you get that, you can extract some interesting information, and then you can use the aggregation the search and percolation, but everything to derive information from the data.
Thanks.
Sure.
Is 2.0 going to be backward compatible with 1.9, or so you can, well, let's say run a few nodes with 2.0 and well, upgrade partially, or you have to reboot your whole cluster?
It should be compatible backwards. We will definitely release that information as part of the release notes. So far, it looks like it will be compatible. The only thing that might be required is before you upgrade, you need to run a special command to find the indices that are really, really old, that were started before 1.0, that might potentially still include some old data files, and forcefully upgrade those. But that will be a documented API and a tool to do that, and it will all be part of the release notes.
Okay, thank you.
Elasticsearch specialist, Honza Král, thank you very much.
Thank you.